Thank you very much. So yes, again, my name is Matt Kirby, and I'm going to give this talk on exploring the possibilities of additive manufacturing for advanced applications, and really what, as I figure out how to work there we go. So really, I'm not only going to talk about exploring the possibilities, I'm going to talk about several different projects that we've worked on for specific applications, but the other thing that I'm going to do is try to talk a little bit about some of the gaps that we see and we're trying to address with this technology. And then also, what are we trying to do in the future? So before I dive into maybe those things, I'm going to tell you a little bit more about Southwest Research Institute. So we are a large nonprofit independent research organization. So by independent, what I mean is that we're not affiliated with the university or with the government. So we're unbiased, if you will. We have about 3,000 employees. Most of them are located at our campus in San Antonio. This is an aerial view of our campus here in San Antonio. We've got over 6.1 square kilometers of facility space and a lot of lab space. And our primary business model is writing research proposals and doing contract research and development. And so last year we did about almost $800 million in contract research and development. And we've got over, around 1,500 patents. We really, though, actually we see ourselves more as intellectual property friendly. So if a company comes and does a research project with us, we're not going to take claim to that. If you're paying for the research, we're not going to take claim to that intellectual property. We do generate some patents through our internal research programs, but we're really more concerned not necessarily leveraging patents or trying to grow our patent portfolio, but really trying to help get technologies to the marketplace. And then we have 51 R&D 100 awards. And kind of how do we see ourselves in the technology space? So this is a simplified, look at kind of how we view ourselves. So, we view ourselves as kind of bridging the gap between basic or fundamental research and production. And so we're not interested in making things for commercial profit. We're more interested in taking a technology that's maybe very promising but not mature, and then helping to improve that TRL level, and then working with an industry partner to commercialize that technology. And so we like to operate kind of in the applied research space is really kind of where we feel like we fit. And we have a tagline. We say we do everything from deep sea to deep space. And part of the reason for this is, so I've got, see if the laser pointer, I don't know if you can see here, but in the top left image is actually a picture of the Alvin submarine. So that submarine has mapped 98% of the ocean floor, including parts of the Mariana Trench in the Atlantic Ocean, and that was something that was designed and tested at Southwest Research Institute. And then in the bottom right image is high-resolution photos of Pluto. And so a team at Southwest Research Institute, we were one of the prime contractors on the New Horizons probe that NASA launched several years ago, and took, for the first time, high resolutions of Pluto, and then it's continuing on out into the deeper, parts of the solar system to take additional data and footage. But today, so there's, I'm not going to read all these different ones off here, but today what we're interested in is additive manufacturing. So what are we doing in additive manufacturing? So it's a little silly here because I've organized things with past, present, and future. And when I say past, I'm going to start with about 2017. So someone's going to laugh at me and say that's not past, but I think that highlights too how fast this technology is moving and accelerating, and also. 2017 doesn't mark the beginning of us researching in this area, but it does mark the beginning of us purchasing our own metal additive machine. And that's also I'm going to talk mostly about metal additive, powder bed fusion. And that was kind of the start of when we purchased our machine, and that led to a lot more synergy within our own organization, because we were doing several projects in additive manufacturing prior to that time, but they were all kind of disparate groups kind of doing these research things. And so then we came together and have this focus of advancing additive, bought our own machine, and that really led to a lot more connectivity within our institute to go after bigger challenges. And so I'll talk a little bit about that, and then I'll talk about present, which is kind of, since that, getting our metal AM machine, where have we really kind of focused on trying to address different gaps? And so I'm going to talk a little bit about qualification of materials and certification of AM parts. And this is going to be a little bit of more of a flavor for aerospace. And then finally, I'm going to talk about the future. So just this year, we've started publicizing this. We're building a $50 million facility it's going to be called the Center for Accelerating Materials and Processes, or CAMP. And this is going to be a facility that has state-of-the-art inspection and additive manufacturing equipment to be able to do basically everything from build to post-process to finished part. And this is not in any way to create the parts and then sell them, but actually to do research on this whole process of production with additive. So the past, and maybe I should back up here if I can, and just show, this is that machine. So this is our humble beginnings here when I'm talking about us being involved in additive. This is our initial Renishaw AM250. This is our initial additive manufacturing lab. So kind of just a small little space that we've carved out. And so you'll see as I talk about future, how far we've come in terms of investing in this technology and trying to solve some meaningful problems. So the past. So I mentioned with the purchase of our additive manufacturing machine, that really got us engaged with, or really got us as an institute internally really connected with who's doing what in additive, how can we have more synergy. And we actually did an internal research program, a $1.4 million internal research program called MAKERS. And that was metals, additive, kickoff, emphasizing research synergy, MAKERS. But the idea of this, again, was create synergy and work together to tackle bigger problems than just being a bunch of little units going after these smaller projects. But we also wanted to demonstrate, we wanted to learn and demonstrate our capabilities. So we invested in 7 funded projects. This was actually a process where we had people propose research ideas. We had, I think, 22 submissions. We had 11, we had a panel review those submissions, 11 invited proposals, and essentially boiled that down to 7 funded projects from various applications. And so I'm going to walk through very quickly each one of those, but that we really felt like this sort of kickoff program leveraged a lot of our core competencies. And I won't read all those off, but I'll just highlight a couple. In material science, we have a world-class surface engineering group. And then we do a lot of modeling, computational modeling, life prediction, and then as well as non-destructive evaluation and structural testing. And so I'm going to jump into each of those 7 projects. I'm going to hit those pretty quickly, but just to kind of show you how we were starting to build this breadth of understanding in additive, and we were able to springboard from that. So the first one here is our first project was utilizing additive manufacturing to enhance liquid cooling, and this is an automotive application. And I'm sticking to my cards because hopefully this mic's not on, but I'm sticking to my cards here because I don't want to spend too much time on each of these. But if you have questions, please let me know. I can get you in contact with the people that worked on these projects. I was involved in this MAKERS program, but I had, and I'll highlight the specific project I was working on. But this is an automotive application, and it's for cooling of cylindrical heads. And so that's really limited to geometries that can be formed with sand cores or drilling between cord sections. But in region where there's high heat flux, there's still an issue with enhanced cooling, and you can really only do that with increasing the velocity of the coolant. And so one thing this was looking at was if it's possible to utilize different geometries, which are kind of shown there on the top left, to enhance cooling. And so you can also see some kind of simulated images that we have here. But we actually went through the process of building these different geometries and then testing them to see can we use these unique geometries to enhance cooling that can only be manufactured with additive. And so we actually had some pretty good success here, and I believe we got some follow-on research from this project The second project is also related to internally cooling, but this is for radial turbine blades or turbines using additive manufacturing. And so really the efficiency of radial turbines is you can increase that through increasing operating temperature. But then obviously you have to have the material, you have to have some enhanced cooling in order to run at those higher temperatures. And this is for power generation. And so one of the ideas was, conventional manufacturing methods such as investment casting use internally cooled axial turbines, but that's really difficult to apply to radial turbines where it's manufactured as a single piece. So again, we've talked a lot about how unitized structures is a big, reason to potentially use additive. And so this was a case where we wanted to do that, but we wanted to build in those cooling channels within the turbine itself. And so we still have work related to this particular, in this particular area based on some work that we did in this project. And so you can see kind of some of the cool images of the turbines actually built on our build plate, and then some of the simulations that we did. And I'm not showing, but we also did some testing to evaluate whether those internal cooling channels, if that was successful. Third project, this was more actually, I mentioned we like to stay in the applied research space. This was actually a little bit more maybe basic or fundamental. So this is additive manufacturing for shape memory alloys, and this was really interesting. This is a nickel titanium material, and this is a unique material. It's demonstrating, it's got good shape memory or superelasticity properties. But the challenge is you can't, it's really expensive material. You can't get a lot of this material. And so again, additive's really good, right, we minimize waste. And so this was an opportunity to use this material, but also use the additive process. You got a lot of knobs to turn with the additive process to tune the parameters to get the properties that you want for different shape memory behavior. So this was a lower TRL. We have not transitioned this to much of a higher TRL. It was a really interesting project, more high risk, high reward, and we showed some capabilities here, but still more research to actually this be something more commercially or production available. So then number 4, this is a space application. So this is additive manufacturing for hermetic metal ceramic bonds. And so one of the issues with metal, so this is for space applications, weight saving is a big issue here. And one of the challenges when you're creating a metal ceramic bond is that you have a lot of interfacial stress due to the differences in the CTE, the coefficient of thermal expansion between these two materials. So the question was, can we, again, idea of unitized structures, can we actually build on top of a ceramic material using the AM process and just tailor the AM process to get the bonding that we need to reduce that interfacial stress? And so that was, we do a lot of work in the space sciences industry, and so that was something that was really interesting to our partners and interesting to NASA. And so you can see some examples of the builds on top of those ceramic pieces on the build plate, as well as some modeling that we did to try to optimize the parameters before we went to the build process. This one, number 5, is kind of interesting. It's related to producing powder. And so what this is it's kind of a new way to produce powder in these very interesting sort of hexagonal platelets. And the reason for this was we had a process where vacuum roll coating that we could use, where we could basically create that hexagonal pattern on the vacuum roll and then essentially stamp that onto the material. And so the advantages of this would be things, or we thought the advantages would be things like you can also coat this material and then create those platelets, and so you get some interesting properties in your additive process through surface coatings. But then also you could get some better packing density if those platelets were aligned. And then the manufacturing process was actually pretty simple. This one, we actually ended up filing a patent, I believe, so we do have some intellectual property there. There were some challenges, though, with this in terms of transitioning this, because those platelets, they have to be properly oriented to get that good packing density. Otherwise, you have a propensity to have maybe vertically aligned platelets, and that can create additional voids and defects. And so additional work to be done here, but something that a very efficient process to create powders of unique metals. And then this one's really near and dear to my heart. This is the one that I worked on. This was related to simulating the selective laser melting process and trying to predict residual stress, as well as average grain size, other microstructural volume fraction, and use that ultimately to go from property to performance. And so the impetus for this project was that we were kind of focusing on the U.S. Air Force. We do a lot of sustainment for them. There's a lot of times where they have old aircraft. We're thinking of maybe the A-10 is a very old aircraft, if you're familiar. And so a lot of times when they're trying to extend the life, they might have a part that they need, and they'll go back and find, well, the manufacturer doesn't exist anymore. Or the mold for the part is who knows where. And so one of the things we were trying to do here is, can we build the part right the first time by being able to predict residual stress and minimize that in the build? And then trying to see, can we redesign actually an aerospace component with this sort of framework? And so we actually had another, it's not shown here, but these are just test specimens to see if our model, how well it did at predicting residual stress. But we also redesigned an aerospace component to see how well our design compared to our modeling compared to what we actually ended up building, and if we could build it right the first time. And then finally, I believe this is the last one here, is NDE for additive manufacturing qualification. So obviously NDE is incredibly important in the additive manufacturing process. And so one of the things that we were trying to do is see, how does surface roughness impact your ability to detect flaws? And so we actually placed some flaws specifically in our material. And then we also wanted to see, is it possible to predict bulk properties based on something like ultrasonic testing, and then use eddy current for defect detection. And so that's a project that we've been able to leverage to get more involved in kind of the NDE aspects of within the research community. So now I just want to quickly, that was kind of I know that was a lot of information. So that was kind of establishing, hey, we've got some core competencies, this breadth of things that we can do. And what we wanted to try to do then is leverage that to get externally funded projects or additional internal projects. And so one of those was creating this process pipeline. And I kind of mentioned this, going from process to performance, and kind of these different models that you need to get there. And so we've already seen kind of thermal process modeling of how does that really localize energy that's input by the laser. How do you feed that then into something like a thermodynamic model to predict things like average grain size or other microstructural features? How does hipping, how does that influence the microstructure? Volume fraction. Can we then, from the structure, predict, for instance, a stress-strain curve? And then can we predict residual stress? Can we predict yield stress? And can we understand what's the uncertainty in our prediction capabilities? And then finally, can we use those models to actually predict damage, fracture of the material, life prediction? That's really important to aerospace components when we're talking about fatigue. And so I'll touch a little bit more on this last piece of life here in a minute as far as certification goes. But first, kind of, where are we presently? So we did all that stuff kind of at the beginning to gear ourselves up for helping. Again, we want to help solve problems to make additive manufacturing more effective for others, for the community. And so one of the big gaps we see right now is qualification of materials, certification of parts. So the cool thing with additive manufacturing is that you're creating the material and the part at the same time. The challenge is you could come up with this incredibly unique material system that, something that's, I'm thinking even in the ultra high temperature material space, there's a lot of, desire to use novel materials, but the process to get a new material qualified is at least 3 or more years to actually get something, and that's on the low end. And so how can we use something like that the process to performance, the ICME modeling framework? How can we use that to reduce risk in new materials and also understand how do we streamline the qualification process. And so, so what I'm showing here in this picture on the left is the that's kind of the building block approach. So you know, normally for qualification, certification, you have all of this testing that you need to do, and it becomes very costly. And then on the right, I'm showing just kind of a schematic of all these different models that we've put together and the associated data to make a prediction about part performance. And so one of the things that we do in our group specifically is probabilistic analysis and understanding the impact of uncertainty. How do different models and our data, how does that influence the uncertainty in our performance prediction? And so we did a project with DARPA to demonstrate using this framework and using this, you know, uncertainty quantification to rapidly qualify materials. And so the idea was, you know, we've got all this, we're going to get a lot of test data, but how do we, in some cases, how do we reduce that test data? But maybe that's not something that's of interest, but how do we streamline that and really focus in on where do we need to gather more data to really move this qualification process forward faster and not spend our time focusing maybe on areas where we don't need additional destructive testing for, you know, for particular properties because we're very confident in those. And so we came up with a framework and an approach to qualifying a material and understanding how that uncertainty again impacts qualification. So I won't go through all of those different, you know, boxes there on the right, but essentially what we're trying to do here is give guidance to when do you need more data? When is your probability of, you know, a particular design criteria? When is that going to be meet your specification? Or when do you need process control? Or when maybe do you need design change? So this was a really successful project for us with DARPA and has led to some additional work in this rapid qualification area. And again, I kind of mentioned this earlier on the slide. The goal is not to eliminate testing necessarily, but the goal is to perform the right tests and then use the data effectively. And so the ICME model hierarchy is a powerful way to combine sources of information to express our overall state of knowledge and quantify the confidence in our ability to predict performance. So the other piece of this, so that was rapid qualification, maybe of a new material system. The other piece of this is, you know, we've talked to, one of the panelists earlier said that, you know, in 2030, 10 to 15% of all aircraft components are going to be additive manufacturing, made from additive manufacturing. But one of the big gaps we see is actually using critical parts made from additive manufacturing. Because we're thinking of this technology, you can think of it like you're making miles or kilometers of welds. And typically in a structure, where are we most concerned about defects? In the welds. So we can be really creative with this technology, but you can also generate a lot of defects. And so the idea is, how do we show that a part is structurally capable of being used in a critical application? Right now, I don't know of any really critical applications that AM parts are used on aircraft because we don't trust them. We don't trust them in fatigue. And so the idea is, so the long story short is that probabilistic damage tolerance, we think, is one way to help address this problem and in some ways close the design loop. So this is already being used. The FAA, the Federal Aviation Administration, already uses this for aircraft engines. You have to go through a probabilistic damage tolerance assessment to certify an aircraft engine, and you have to meet a certain risk level, and thankfully it's a very low risk level. But this is a very mature method that gives us a probability of fracture, and then we can compare that probability of fracture against a design target reliability to determine a part safety. And we can do this for a variety of different geometries where it's not clear exactly where that critical location is. So instead of putting a flaw in one location and saying, okay, we know this is the critical location, therefore we design everything around what kind of flaw can this location survive, we actually put essentially flaws everywhere. And then we say, and it's a conditional probability where you say, okay, I have this flaw, what's the probability of fracture for this given flaw, you know, but then what's the probability of actually having this flaw in this location? So there's some additional testing to get some of this information, but the idea is it could really be used for additive manufacturing. We think that probabilistic damage tolerance is a viable methodology methodology to assess the structural integrity of high criticality AM parts for aerospace applications. So we think this is a huge gap that needs to be addressed if we want to see the number of AM parts go up from, say, 10 to 15% to even higher, and actually be used for critical applications, not fuel nozzles, for instance. So how we're kind of helping in this space is we actually have a commercial software called Darwin, damage assessment of risk with inspection, and it's a software we've been developing since 1995. We've worked really closely with the FAA, again, specifically for aircraft engine certification, but now we're trying to work with the FAA to apply this to additive manufacturing parts. And I said close the design loop because then you can go through this process of design, simulation, get to your certification or get to your probabilistic damage tolerance assessment and feed that back into how can I reduce that risk in my design. So kind of make this design feedback loop. We've had continuous funding for this software since 1995. Again, it's commercially available. We've had about $50 million in funding, and it supports 2D, 3D models, a variety of different inherent and rogue anomalies. And this is, so again, the FAA says, hey, you have to use a probabilistic damage software tool. They don't tell you which one to use, and there's certainly others, but this is one of the ones that's widely used across the aerospace industry to do that probabilistic damage tolerance assessment. So those are some things that we've really been focusing on. Well, and I say there's some other things we've been focusing on as well. I kind of focus my talk on those because I'm a little bit maybe closer to those, but I think those are real gaps. The material qualification, part certification, those are important gaps we're gonna have to overcome because I think this technology can be more than just rapid prototyping. I think that's a good use of it in a lot of cases, but I think if we want to get to unitized structures that actually have meaning, we're going to have to figure out how to overcome these certification challenges. So the future. So I already kind of mentioned this a little bit earlier, so I kind of let the cat out of the bag, but we are building a new $50 million facility, 3,300 square meters, dedicated to the vertical integration of manufacturing processes to accelerate learning. So essentially learn faster by bringing everything, the schematic on the bottom, by bringing everything under one roof and essentially creating a pilot production facility where what we like to think of is powder comes in one side, finished part comes out the other side. And we're sparing no expense and trying to set up this facility, and we already have some committed contract work with the Department of Defense to build specific aerospace, to research specific aerospace component production. Again, we're not trying to make these parts and then sell them. We're trying to use this as a platform to help make people more effective with additives. So supporting industry can, potentially use this sort of pilot facility to work on their design or understand post-processing. I guess I'll point out too, there's the picture there on the right, kind of in the middle, and that is the CT machine that we're going to have in this facility, and it's one of the largest in the world, 9 MeV, and so we're going to have some pretty cool toys to play with in this facility. And that's supposed to break ground in either the end of this calendar year or 2024, beginning of 2024. That's just kind of a commercial rendering of the building. And it'll be a secure facility as well, so we can do classified research if necessary. So these are the 2 AM machines that we're starting out with in that facility. We certainly have desire to grow the additive manufacturing capabilities within that facility, but we've got two EOS IAMSM machines with different build volumes. And so the one on the right is got a build volume with a height of about 1 meter, so a pretty large machine, and it's got 4 lasers. And so one of the things that we want to do with these machines is some initial research topics is understanding how do you go from maybe a smaller scale to a larger scale machine. Again, we've already got a contract with the DoD to look at real aerospace parts, or the manufacturing of real aerospace parts, and researching that. And so we're going to be able to research with some state-of-the-art materials and processes, We're going to be able to explore part consolidation enabled by that larger build volume. Some additional research topics. This was something I always think is interesting to me and in some ways kind of trivial, is the process of depowderizing after you create a powder bed fusion part. So in some of these complex parts, you can get, you've got material that hasn't melted and it's stuck in the part itself. And actually that process for some organizations can be a big schedule burden, because you're depowderizing, then you need a CT to see, did you get everything out? And then you need to go back to depowderization. And sometimes if you don't have the CT in-house with enough power, you have to ship that out. And so this could be multiple iterations. So what we're going to try to do is, since we have that all under one roof, is use this as an opportunity to learn how do you depowderize more efficiently to prevent that need to keep going back and forth. Optimizing robotic laser welding techniques, improving thermal barrier coatings. I mentioned we have a world-class surface engineering group that does a lot of coatings for ultra-high temperature materials. We've talked about it today with the Women in Material Science panel about building good databases, material databases, and then using artificial intelligence or other means to explore those databases and develop new materials. And so with that, I think the last thing I want to leave you with is just that we want to collaborate with you. So we are a 100% contract research and development organization. And so we want to help people be more effective with additive manufacturing. We don't want to take your place as a production. We don't necessarily want to do a ton of basic research. We want to be that bridge in the middle of how can we help make something useful with additive. So my contact information's there. I'm happy to help, and I presented a lot of different things. Some of them I wasn't necessarily personally involved with, so I will definitely get you connected to the right person if you have any questions. So with that, I thank you so much for your attention and welcome any questions.
Thank you, Matthew, for this amazing presentation and share with us this amazing application that really inspired us here in the Institute. So now it's time for the Q&A session. So anybody here in the audience has any question for Matthew?
Just quick question. Did I understand correctly that you are, kind of developing software for fracture prediction, like in the long term, under fatigue conditions, for example? I'm working for battery industry, kind of sharing similar interests for fractures, plastics, composites, for example, in order to understand the predictability of fracture, to know when particular materials or design features, corner or something like that, can help us to be more predictable in terms of avoiding those kind of features.
Yeah. So yes, we do have that Darwin commercial software, but it is right now specifically for metal. Because it relies on linear elastic fracture mechanics, where you've got a homogeneous isotropic material. We could talk offline about composite fracture. It's a lot more difficult, but in this case, we're working with metals, and we've got a library of stress intensity factor solutions that we can use, but only for metallic components at this point.
Any other question from the audience? Over there.
I'm particularly interested in the hexagonal powder that you had produced. I was going to originally ask what the particle size distribution was, but it's monodisperse. So can you just comment on the size of the powder, and then any sort of, let's say, bed density studies you had done to see if it was as, laminarly as effective as you thought it might be?
Yeah, so I can't remember. So what I'll say is, I can't remember exactly what the size distribution was. I can get you that information, but I can't remember off the top of my head. But I know that we played around with different, based on your stamping pattern, you can effectively get different size distributions, and we could show that you could essentially get essentially less tails out, you could crop off that sort of distribution. And then your other question was about kind of the laminar behavior of the platelets. That was the biggest challenge. So it was, that's where the research for us needed to go next, is because you could lay the powder down, but it was really hard to actually get it to lay like we had envisioned it. So that's where you got additional defects and things like that. So I don't know, we'd have to solve that problem before it would probably be a viable solution that could transition to a commercial solution. So that was a significant challenge. Does that answer your questions? Okay.
Is there any other question?
Thank you, Matthew, for your question, for your talk. Very nice. But I have some question for you regarding to the residual stresses. I noticed that you have some mathematical models to predict those. In the past, we were working with a big aerospace company to make the prediction of those based on a standard that's coming from NatCap, and that is based basically on experimental tests and so on. So I'm just wondering, what is the percentage of error and the reliability that you have based on your numerical analysis to predict residual stresses? Because if it is a repeatable process, so maybe we can avoid in the future to go to the experimental setup.
Yeah, no, that's a really good question, and I think yeah, I'm trying to think how I want to answer that, because yeah, that's one of the things that we looked at, was just doing a deterministic prediction, and I think that one thing I want to say as a caveat is you're going to have maybe some different challenges with different geometries. So when we were just predicting that sort of caterpillar-looking structure, that's a standard NIST specimen, and it's actually designed for predicting residual stress. You can or testing residual stress. With our deterministic predictions, we did a pretty good job, with the caveat of calibrating a couple parameters. What we wanted to actually do was do a full probabilistic study to see what's the uncertainty in actually those predictions, because there's a lot of knobs you can turn. And then I think, so that was your question on, so yeah, I guess I'm not doing a great job of answering questions, because I can't tell you exactly what percentage of error we got in those predictions, because we had calibrated those properties and then we didn't do kind of a full probabilistic assessment to say what's kind of our error. But there was another question that you had after that.
Well, what happened is the idea that you have here is fantastic, because if we can avoid the post-processing that is required for additive manufacturing parts, that would be great. Specifically speaking about the hipping process, that is really expensive one, and if we can avoid it, would be great. So you have something very valuable. Absolutely.
And another thing I will say too is our intentions were even less, less interesting than maybe that, avoiding hipping. It was really, when you go to build a powder bed fusion part the first time, I think a lot of people, think that you can just, build your CAD model, set it and run it, and there's a little more nuance to it than that. You can certainly have some issues with residual stress that prevent you from even building a part, and then once you go to take that part off the build plate, does it deform so much that then you can't use it in an assembly? So we had some even before thinking about the hipping process, which is a really good point. Can you get beyond that hipping process? We were even just thinking, can you build it right the first time, so when you take it off the build plate, it doesn't deform on you and become useless?
So. Well, thank you very much.
There is 1 minute more for last question.
Hi, it was very interesting, your talk. And I have one question. Do you have any projects regarding nanotechnology?
So related to additive manufacturing, we do have, so for surface chemistry, our surface chemistry group, they have some coatings types of, I don't know if they have, I guess I'll be honest and say, I don't know if they have a specific research project right now in additive but they use a lot of nanotechnology in their coatings. So I know that we've done some of that. And then, unrelated to additive manufacturing, we have a project with Tech de Monterrey that's using nanotechnology for a composite application. But so if we were to have a nanotechnology project, it would be our surface chemistry, developing novel, surface coatings. They would be the ones that I would believe would have kind of a solution, because they've used that technology in the past for other surface coatings. So.
Thank you very much.
Okay, one last question.
We are trying to develop a platform to accelerate the development materials, and we are struggling to the databases, the materials databases. How you are building the materials databases so it's useful for forecasting the analysis of the performance of the materials. Are you thinking about it, or are you doing something related to that?
Yes, we are thinking about it, and so the first thing I'll say is I will make sure to get you in touch with the person that's running. There's a project we actually have that's very related to what Mariana was talking about, where we're building a database for refractory metals, and then we're trying to explore that with artificial intelligence. And what I'm failing to remember, though, so we have some capabilities for producing really small samples and doing some high throughput characterization, and so that's how we're kind of building that database. But what I'm failing to remember is some of the technical details that I think would be important. So what I will do is, yes, we're concerned with that as well. And obviously with artificial intelligence, maybe it was said, but a lot of times you need a lot of data to be able to make a good prediction. So some of the things that we've done in the past have been, can you inform those artificial intelligence models with physics to help constrain your solution space? But then also we've got to have high throughput experiments. So we're doing this on a small scale.
Just to close the loop, right? Because you have to do the evaluation analysis of the performance of the physical performance of the material, and then feedback on the loop to the database.
So right now what we're focused on is kind of the first part of, can you go from predicted design to can you actually create a material that gives you the properties that you thought it was going to give you at a small scale. And then the next step would be, once we can prove that part of the small process out, is then go to build the part, and can you get from performance all the way back. So right now we're really in that first loop of, can I design a material, and then can I actually build it, and then does it actually give me the properties I thought it was going to give me? That's kind of where we are focusing on this project right now with the refractory metals.
Once again, Matthew, thank you very much for your presentation.
Thank you.